So we are happy to have back at NYU Dr. Shota Komatsu from CERN. He has done all his studies at the University of Tokyo, if I am
Yeah, sure,
right.
yes.
And after a postdoctoral at the Perimeter Institute and a period at the Institute for Advanced Studies, he joins CERN for a 5-year position, right?
Yeah.
One that was 6 years in the past, in September 2020. We are very happy to have him with us today. He will talk about solving four-dimensional gauge theory using two-dimensional techniques. Thank you.
Okay, thanks for the introduction and thanks for having me. So I'm going to talk about some review about some exactly solvable four-dimensional gauge theory, which is based on the two-dimensional techniques. And actually, like I already I gave a similar talk a few weeks ago, and I will include something new. But like for those who already heard that talk, there might be some overlap. But I will try to avoid at least making the same joke. Okay, so let's start. So this talk, I said like about gauge theory, but it's also about string theory. So when you hear the word string theory, I guess like the common view of the string theory is that like, okay, it might be a theory of everything, or it might be some theory which is most fundamental. Or maybe the critics might say that it might be theory of nothing, but I won't address that critics. But anyway, like one thing common in all these viewpoints is that like these viewpoints are kind of viewing like string theory as a kind of ultimate form of reductionism. However, in this talk, I want to kind of advocate a different viewpoint of string theory, in which we view string theory as some kind of emergent phenomena, like in condensed matter system. And in particular, I want to emphasize that the strings actually emerge from gauge theory. So in order to talk about that, I first need to give you a brief introduction of the gauge theory. So the gauge theory is one of the most fundamental framework of modern theoretical physics. And as you know, like in nature, we know like there are four fundamental forces: electromagnetism, weak interaction, strong interaction, and gravity. And among all those among all those four, three of them are described by gauge theory. Well, to be honest, like gravity is also in some sense a gauge theory, but the gauge theory that I'm going to talk about today describes three of the four forces. And in particular, well, among those three, the first two, electromagnetism and weak interactions, are actually relatively easy to study analytically. And for instance, there is an impressive computation of electron anomalous magnetic moment. And this is basically like how electron behaves under the action of like some electromagnetic force. And this is we can say that this is the most accurately verified prediction in physics. And there is a computation by theory done by these people in 2012, which predicts this number. And on the other hand, there is an experiment which basically confirmed this number. And you can see like the two numbers match up to very, very high precision. And this computation is really, really like heroic efforts, because like in terms of Feynman diagram, it actually you need to sum more than 10,000 diagrams. Okay, so on the other hand, the last of the three, the strong interaction is much harder. And and the one reason why it's hard is because strong interaction is known to be like strong in low energy. And for instance, like we know protons are made out of 3 quarks, but and also we know like what is the equation governing the quarks, which is basically quantum chromodynamics. But still, we don't know like we can compute many properties of proton, such as size of the proton or mass of the proton from first principle. And I should also add that and also like a confinement and mass gap is a millennium problem of the Clay Institute. And given this situation, I think it's fair to say that we need some better idea or a better method to understand the strong interaction in gauge theory. And one idea that I'm going to emphasize to today's talk was proposed originally by de Vooght. So in order to explain that idea, let me just briefly review the basic fact about the gauge theory. So in the gauge theory, the fundamental object is of course the gauge field, which carries like Lorentz indices. And in addition, in the case of QCD, it carries two indices, and each of which takes like from 1 to 3. And roughly speaking, you can view this gauge field as kind of like a 3x3 matrices. And in 70s, de Vooght pointed out that things simplify drastically if one replaces 3 by n, and then further take n to infinity limit. So that's why I put this title, more is different. But in this case, like more is different and it's simple. And so this limit is called large n limit. To explain why it simplifies, why things simplify in this limit, let me just briefly review the basic fact about the large n limit. So for that, it's useful to recall the Feynman diagram. So this is one of the basic, simplest like Feynman diagram, which describes the splitting process of one particle into two. And in the computation, we multiply this Feynman diagram by a factor of g, which is a coupling constant. And if you want to draw the same kind of diagram for the gauge theory, because the gauge field carries like extra 2 indices, so it's kind of natural to consider the flattened version of the Feynman diagram, which consists of like 2 lines. So this is called a double line notation, and this comes with the Yang-Mills coupling constant. And one important feature of this diagram is that in the large n limit, each loop gives a factor of n. For example, let's consider the Yang-Mills version, a double line version of this like a vacuum diagram, so which is given by this. And as you can see, this contains like this red loop and also green loop. And each of the loop for each of the loop, you have like n possibilities of the colors or indices. So in total, you get n squared. And let's also consider the other diagram. So this was the diagram that I already talked about. And you can also consider this kind of diagram, so which now contains like 2 interaction vertices. So this diagram contains 2 interaction vertices and 3 loops. So that's why I get this factor. On the other hand, this diagram also contains 2 interaction vertices, so you get GMO squared. But if you count the number of loops, then okay, so you go like this, and like this, and like this, and then comes back. So you actually only have 1 loop. So you get like factor of n. And the large n limit is defined by this limit. So you take n to be large, but at the same time, taking this combination to be fixed. And if you take this limit, then you can immediately see that this last diagram drops out because it doesn't come with a factor of n squared. And more mathematically, you can understand which diagram contributes in the large n limit in terms of the topology of diagram. And in particular, the diagrams that contribute at the leading order are diagrams that can be drawn on a sphere. On the other hand, the diagrams that contribute at the next leading order are the diagrams that can be drawn on a torus. So these are like examples. So for this diagram, which contributes at the leading order, you can draw on a sphere. Whereas this diagram, because of this like cross, you cannot draw it on a sphere, and instead you need to draw it on a torus. So it's a little bit probably hard to see that these 2 diagrams are the same, but if you think a little bit more about it, then you can see that these are the same. And in particular, the diagrams that can be drawn as sphere, we call them planar diagrams. Okay. So there are several like advantages of considering this large N limit, which is a kind of like generalization of the QCD. First of all, this large N limit allows us to have extra expansion parameter, which is 1 over n. And furthermore, expansion can be organized in terms of the 2D surfaces. And this fact suggests that there should be some kind of alternative description of the gauge series in terms of two-dimensional system rather than like a four-dimensional field theory. So this idea is quite old and already pointed out by Tufut around the 70s, but the theory described in the surface remained mysterious for a long time, although there have been some progress for the simple like a matrix model around 80s and 90s. But the situation changed dramatically when Modasena proposed ADS-CFT correspondence in 1997. Basically, ADS-CFT correspondence gave us a concrete proposal about what the 2D theory is. So in particular, the one prototypical example of ADS-CFT is the duality between n equals 4 supermills, which is a kind of supersymmetric gauge theory in 4 dimensions, and string theory on a particular curved background. And as you know, the string theory is a theory of strings, so it is basically described by 1 + 1 dimensional theory. And furthermore, in 2002, Minahan and Zarembo found that there is actually this 2D theory also has an alternative description in terms of 1 + 1 dimensional spin chain. So this is also 2D system, but here we have some continuous theory, but here we have like a discrete system. But the claim is that they are actually like the same, they describe the same system, but they are just like a different descriptions. So these connections to 2D theory and spin chain turned out to be quite useful for the actual computation, and in particular, because of the property called integrability. So this is the main topic of my talk. So let me just explain what the integrability is, and also what the connection to Yang-Mills theory is. So n equals 4 supersymmetric Yang-Mills, which I abbreviate in this way, contains a bunch of fields in addition to gauge field. So it contains gauge field, of course, because it's the Yang-Mills theory, and also scalar and fermion. And the point is that because of the supersymmetry, all the fields are related by the supersymmetry, which basically means that all the fields are in the adjoint representation of UN gauge group. So therefore, you can view all of these fields as some kind of n times n matrices. And given these fields, one simple way to build a gauge invariant observable is to multiply those fields and take a trace. And because gauge transformation acts in this way, you can immediately see that this is invariant under gauge transformation. So let's take like this kind of like expression, which we call single trace operator, and then try to compute a 2-point function, and then using the double line notation. So if I do the usual weak contraction, like this is a tree-level computation, then I get this diagram. So I just like have O1, which contains 3 fields, and O2 has 3 fields, and like this. And of course, if I start including interaction, that you need to include much more complicated diagrams like this. But the point here is that in the large N limit, the diagrams that contribute all has the topology of the cylinder. So if I fill in all these faces, then I get like this cylinder structure, where this direction can be viewed as a time. So this basically tells us that there should be some emergent 1 + 1 dimensional system. And Fortunately, for the case of n equals 4 sigma mu theory, this 1 plus 1 dimensional system has a nice property, which is precisely called integrability. So let me just try to be a bit more precise about this point. So for simplicity, let's consider this single trace operator made out of only with two kinds of scalar fields. So, and then let's zoom in one of the operator. So I have and as an example, I consider this phi1, phi2, phi1. And if I draw a leading quantum correction, for instance, then I have this gluon exchange diagram between these two fields. And you might think that you can also draw this kind of diagram, but this diagram is not allowed because it's not a planar diagram because of this crossing. So other diagram that survive in the planar limit is this diagram, which comes from the contact interaction of these scalars. And unlike this gluon exchange, the endpoint of the contact interaction has two possibilities, either phi1, phi2, or phi2, phi1. And one important finding by this Minahan-Zarembo paper is that all these leading quantum correction can be mapped to the action of some kind of spin chain Hamiltonian. Once you map phi1 to upspin and phi2 to downspin. And furthermore, this Hamiltonian turned out to take this form, which is the simplest possible spin chain Hamiltonian, which is often called Heisenberg spin chain. And what is nice about this mapping or relation to the spin chain is that under this mapping, the eigenvalue of the Hamiltonian basically governs the long distance behavior of this two-point function of the operator. And the operator basically corresponds to the eigenstates of this Hamiltonian. And let me also just emphasize that this Hamiltonian is, as you can see, nearest neighbor in interacting Hamiltonian, but that property is tied to the fact that you have a planar diagram, and you are not allowed to draw this diagram. Okay, so let's talk about this Hamiltonian. And this Hamiltonian actually turns out to be rather special. And why it's special? It's special because it actually contains infinitely many conserved charges, which commutes with the Hamiltonian. So this is S local charges. And furthermore, it is known that the eigenstates of this Hamiltonian can be constructed by basically superposing the plane wave. More precisely, by plane wave, I mean expression like this. So I view the downspin as some excitation and then draw some plane wave expression. And then I just sum over all possible ways of this coupling this n to momenta. And this ansatz of wave function is called beta ansatz. And remarkably, this simple ansatz, which only contains one free parameter, which is S, works nicely, and it gives the eigenstate of the Hamiltonian. And I should emphasize that these two facts are actually related. So to see this, let's consider the 3-to-3 scattering of this excitation. Because you have some extra charges, you can act this 3-to-3 scattering picture, some linear combination of these infinitely many charges, and then modify this picture into this picture in which interaction, only 2-to-2 interaction takes place. So this basically, but because we only acted the symmetry generators of the problem, this S matrix should be the same as this S matrix, which basically says that this 3-to-3 S matrix should factorize into 2-to-2 S matrices. And that's why, and then this 2-to-2 S matrix is SP1P2, which appeared in the one slide before. So this is basically the reason why such a simple ansatz worked so nicely in this system. And furthermore, you can also act a different linear combination and modify this picture into this picture. And of course, like these two pictures are the same. And that requirement is what's called the Baxter equation, which gives a very strong constraint on allowed form of S. Okay, so let's now, so this is how you actually relate n equals 4 supermills at the leading order, for the leading order quantum correction of n equals 4 supermills to the spin chain. And let me just make some other comments. So it turns out that the similar relation to integrable spin chain exists also in actual QCD, as long as you only consider one loop correction, and also in some limit of QCD. However, what is special about this supersymmetric version of Yang-Mills theory is that this relation to integrable spin chain holds at all loops. So even after you include all the corrections in the large n limit, there is a connection to the integrable spin chain. So for instance, at 2 loop, you need to include this kind of diagram. Then what you get is some special integrable spin chain with next nearest neighbor interaction. So in some sense, n equals 4 supermills is a kind of generating theory of integrable spin chain, because you can get various different integrable spin chain depending on to what loop order you consider the theory. And using this property, people succeeded in computing the two-point function at finite 't coupling and large n limit. And this was done around 2009. So as long as the two-point function is concerned, this theory was actually solved around 2009. So, okay. Okay, so let me now talk about a slightly different object, so which is more related to what I was working on. So far I was talking only about some like a two-point function of local operator, single trace operator, which is of this form. However, in gauge theory, there is yet another important class of observables, which is Wilson loop. And the Wilson loop is defined, as you probably know, in this way using the gauge field and the path-ordered exponential. So here I forgot the trace, but if you expand the path-ordered exponential, then at the leading term you get 1, and then the next leading order you just bring down this exponent, and at the next leading order you get ordered product of the two gauge fields. And this Wilson loop can be defined in any contour. So unlike the single trace operator that I was talking about, this is a non-local observables. And as you probably know, this is a good order parameter for confinement. And, and it turns out the Wilson loop can also be mapped to some quantities in the spin chain. And that is kind of like the thing that I'm working on, which I'm going to tell you a little bit more today. So the key idea is, well, so this is already like the punchline of the talk, but the key idea is that Wilson loop can be mapped to some kind of matrix product state. So in order to see this, let's consider not just Wilson loop, but the two-point function of Wilson loop and a single trace operator. So this is different from like a two-point function of single trace operator because this object is non-local. And now let me just make one observation. So if you look at this Wilson loop expression for the Wilson loop, which is given by trace of path-ordered exponential, then you might think that, like, if you like remember quantum mechanics, then you might think that this is a bit reminiscent of the time-ordered exponential that you would write for quantum mechanics with time-dependent Hamiltonian. And it turns out that this kind of formal similarity can be made precise by introducing some like a fermionic degrees of freedom living on the Wilson loop. more precisely, you can actually show that this Wilson loop, which I wrote here, can be obtained by the path integral of one-dimensional fermion localized on the Wilson loop. And this fermion has standard kinetic term, and in addition, it couples to the gauge field, and it also has some mass term. Let's also put some mass term as well. And more precisely, what I meant by this symbol is that if you do this path integral, then at the leading order, and then you expand in powers of exponential minus mass, then at the leading order, you get 1. And at the next leading order, you get e to minus m times the Wilson loop, where the trace is taken over the fundamental representation of the gauge group. So this is what people normally call Wilson loop. And if you further expand, then at the next leading order, you get e to minus 2m times the Wilson loop, where the trace is taken over the like a rank 2 antisymmetric representation. This is not necessarily something people often talk about, but this is also like a generalization of the Wilson loop. So you can see that this one-dimensional fermion is a generating function of all the Wilson loops. And so there is one remark I wanted to make. So here I introduce one-dimensional fermion in order to write down some path integral expression for the generating function of the Wilson loop. But there is also a version which uses the two-dimensional fermions. So this is actually known for a while, but I think not many people know about it. So I just wanted to bring this up. So this Wilson loop you can also write as a path integral of two-dimensional fermion living on a surface which is bounded by this Wilson loop contour C. And the action is given by this expression.
Sorry, Shota, may I ask a dumb question? I'm just confused. What makes it dimensionless? Kind of what is this? Because mass is dimensionful quantity. What is the second dimensionful parameter which makes this meaningful?
Okay, so let's see. Okay, so to be precise, well, it's not really natural to call it mass. It's more like a 1D gauge field living in 1D. So this is a gauge field living in 4D, and this is the gauge field living in 1D. And because it's in 1D, there is no like a dynamical, but there is only holonomy degrees of freedom, and this is U1. So I can just fix to be some like a complex number. Sorry, a real number. Okay, so let me just finish this. So this was proposed by Broda around 1990, I think. And this surface is actually can be anything as long as it's bounded on the contour C. Okay, so this was a small comment. And so now let us compute this object using the fermion. So again, we just draw some like a Wilson loop, and we put some local operator here. So this is the local operator O1, one here. And then, of course, like at the leading order, what you just need to do is to do some like Wick contraction. So like using double line notation, I will do the Wick contraction like this. And so here, like the Wilson loop interact with the field in the gauge theory through this interaction. Or if you consider a slightly generalized version of Wilson loop, which couples also to scalar, then like you can also use these vertices. So roughly speaking, you get this kind of diagram. And in between, because you have like a fermion path integral, there is a propagator of fermion. So this picture, roughly speaking, corresponds to this kind of picture. So you have like a phi 1, phi 2, phi 3, which is basically this part is the operator O1. And then like there is some fermion Hilbert space going in the horizontal direction. And then there is some interaction. And the interaction is, the details of the interaction depends on this I, index for the scalar. So if you're familiar with some kind of matrix product state, then you will immediately notice that this is very similar to the matrix product state used in condensed matter literature. Once you map this to like an up-down spin chain, like I did before for the computation of the two-point function. So let me just explain what the matrix product state in case people are not familiar. So the matrix product state is typically used as a variational ansatz for the ground state of 1 + 1 dimensional spin chain. So let's say we want to construct some like a ground state of like a up-down spin chain, and the most like a straightforward but not efficient way is to just like set this coefficient free and then try to like find a minimum of the Hamiltonian. But of course, this is quite inefficient because there are 2 to L degrees of freedom if you consider the spin chain of length L. On the other hand, there is a kind of like an ansatz called a matrix product state, which takes this form. So you take some like a matrix, choose some matrix, M up and M down. So M up and M down, both of which are D times D, and then write down this kind of state. And then you vary the element of these matrices. And in this case, because you only have like 2 matrices and each of which is D times D, you only have like 2 times D squared degrees of freedom. And if this ansatz is good, then it's much more efficient. And of course, the question is whether this ansatz is good or not. But this ansatz is good, is known to be good if the system has short-range entanglement. And another nice feature is that it's easy to incorporate also symmetry and other property that you need to include, that you want to include. Okay, so so let's come back to the problem that I was discussing. So in our problem, so this, as I said, like we also get some expression like this, which basically resembles the matrix product state. And this expression can be viewed as some kind of like overlap between the matrix product state and the spin chain state, which in this case up, down, up. And as I said, this red line corresponds to the Hilbert space of the fermion that I introduced in order to rewrite the Wilson loop. So in the previous figure, in the context of condensed matter, I had one like extra free parameter, which is the size of the matrix. And in this case, the size of the matrix D is given by the dimension of the fermion Hilbert space, which is infinite. So we have like a one-dimensional fermion, but the dimension is infinite. So in some sense, in that sense, like it's a bit unconventional matrix product state, but still like one particular example of matrix product state. And therefore, so the upshot is that the computation boils down to the overlap between matrix product state and eigenstate. Because like for the operator, we want to have an eigenstate for the reason I explained before. And in particular, we want this overlap in a special class of spin chain called the integrable spin chain. And this overlap between matrix product state and eigenstate actually has attracted a lot of attention recently in condensed matter community in the context of quantum quench. And I listed several important works in this context, especially in the context of integrability, integrable spin chain. And the reason is that people wanted to use matrix product state, which is the short-range entangled state, as some kind of initial state of the quantum quench dynamics, by which I mean like you take matrix product state and let them evolve using the integrable spin chain Hamiltonian. And if you really want to compute it, one way to compute it is to decompose it into the energy eigenstate and then just multiply the energy factor. And clearly, you see that like this overlap plays a very important role in this computation. And so what we found for the n equals Forsyth-Mills and Wilson loop is that when the contour C is circular, we found that this matrix product state actually has a very, very special property, which is called integrable matrix product state. And I'm not going to give you a detailed definition of the matrix product state, integrable matrix product state, but the point is that this is some particular matrix product state which are annihilated by like infinitely many odd conserved charges. And this property actually seems to persist at finite lambda, so not just the tree level, but even after including the interaction. And using this property, one can compute this two-point function exactly at finite 't Hooft coupling, at finite coupling constant, using what's called thermodynamic beta ansatz. Okay, so this was more recent progress in this business. So I was a bit fast probably, but let me just come to the conclusion. So the conclusion is that the large and gauge theory has a surprising connection to string theory and to the system, in particular spin chain. And in particular, n equals Forsyth-Mills theory has a remarkable connection to integrable spin chain. And various ideas and techniques in condensed matter literature make unexpected appearance, for example, beta ansatz and matrix product states. And let me just end with the future directions. Of course, like one question one can ask is how far can we push this program? For example, so far I only discussed the two-point function of single trace operator and the two-point function of one Wilson loop and one single trace operator. But you can ask like whether we can compute all the observables in n equals Forsyth-Mills theory by extending this idea. Or more, in other words, if that's the case, n equals Forsyth-Mills theory is going to be something like Ising model for 4D gauge theory. And another question one should ask in the future is what can we learn about more conventional large n Mills theory rather than this special supersymmetric Mills theory? And there are a lot more questions to be asked, but let me just end here.
Okay, thank you very much for this overview. So now we have plenty of time for questions. So, anyway, okay, I see Sergey has.
So, if one wants to compute the two-point function of Wilson loops, how is it is to extend from this two-point function to Wilson loop and single trace operator?
Yes, so it is possible to do it. So basically, like, well, I think like that can be understood from this picture. So as I said, like a matrix product state is the Wilson loop, and the operator is eigenstate. But if you want to compute a two-point function of the Wilson loop, you basically just need to compute like a overlap of two different matrix product state. And one, I don't know how to directly compute it, but you can always like insert a resolution of identity and decompose it into the eigenstate.
Mm-hmm.
Thank you. Right. You have other questions? Well, one, let me ask this, the local operators that you considered were single trace, right?
Yes.
So what can you do for the multi-trace operators that are, I mean, are they visible in this limit or they are next?
Yes, the multi-trace operator is also visible. So for example, if you consider 4-point function of single trace operator and then expand using the operator product expansion, you will be able to see the multi-trace operator, in particular double trace operator. So now the question boils down to computing the 4-point function of single trace operator, and that can be done using integrability techniques. And that's also something that I developed in the past, although I didn't talk about it today.
Thank you. Other questions?
Hello. Yes, I have a very naive question, but I mean, I don't know too much about this, but the problem we find for confining theories is that when the energy scales are very low, basically we cannot do a perturbative expansion. Is there an intuitive picture why going to the Ising model and redefining the problem is in terms of the Ising model, a quantum theory of spins, can solve the problem of having physics with confinement? Why this would solve the problems QCD, for example, has? That this picture,
Okay.
why intuitive this picture should help us?
So there are, of course, like a couple of important differences between the theory that I'm talking about and the QCD. First of all, this theory, n equals 4 super Mill theory, is conformal theory, so there is no like running of the coupling. So that's one big simplification. So you don't need to like go to low energy or high energy in order to do some kind of perturbation theory. And right. So and also so in the case of QCD, we expect that the string lives in this like a 4-dimensional space. Like there is some like a flux dB in the 4-dimensional space. But here, in order to see the string more directly, you need to use the ADS CFT correspondence. So the string lives on the ADS side.
So, any other question? I see Ken.
Yeah. So what are some angles of attack you have on non-supersymmetric Yang-Mills theory, like QCD? Like, how do you approach, theories without supersymmetry?
Okay. So yeah, I think there are like a couple of possibilities. One, like a honest or like a straightforward possibility is just like a first solve n equals 4 super Mills and perturb it. But of course, like that might be hard. By perturb it, I mean like using some kind of like conformal perturbation theory. So use n equals 4 super Mills theory as a UV fixed point, and then try to learn something about large n Yang-Mills theory, like say pure Yang-Mills theory. So another possibility, which is probably a bit less conventional, but is to consider a Yang-Mills theory defined in ADS. So put Yang-Mills theory in ADS4. So in that case, like, so as I said, like in the case of Yang-Mills theory or QCD, we expect to have a confining string in this 4-dimensional space. So if I put the Yang-Mills theory in ADS4, then we again get a string on ADS4, like a confining flux tube on ADS4. And then I can try to compute the observable defined at the boundary. And that can be studied, for example, using the perturbation theory if the ADS scale is very small. So if the ADS scale is very small, then because it's like considering like small volume or UV limit, so Yang-Mills theory becomes perturbative, so I can just use Yang-Mills and compute it. On the other hand, if the ADS volume is very large, then it's like going to the IR, so I can use the effective string description to compute some observables. And the nice thing about this ADS setup is that like by changing the size of ADS, you can actually like continuously go from the this perturbative Yang-Mills description to this effective string description. That's one direction I'm thinking about these days.
So is it known that there is no phase transition as one changes ADS radius?
Well, there's no definite conclusion, but so there are like Okay, so there are two different boundary conditions that you can choose for gauge field in ADS4. And if you choose one of them, which is called electric boundary condition, people expect that there is a phase transition. But if you choose the other one, then it's possible that there is no phase transition. And by the way, the other boundary condition corresponds to having the gauge degrees of freedom also at the boundary. So it's like a setting free boundary condition for the gauge field.
Wouldn't that be something like a non-critical string, duality, holographic duality for non-critical string, what you just described, and how much is known about that, I guess.
Let me think. Yeah, maybe to some extent.
Or maybe you can say that there is also some analog of S5 in that game, which is hiding because it's small, it's still critical, and
yeah,
maybe I don't know. I'm just speculating.
I see. I think the most conservative answer is like this. So now we are considering large linear mills defined in ADS4. Then maybe there might be yet another holography. So so it's, I don't know, it's some even higher dimensional space in which this theory is described by some fundamental string theory. And that theory may have some extra dimensions.
Right, but then duality you would infer probably from that higher dimensional theory, I guess.
Right. Yeah, that's more conventional ADS-CFT, I think.
So in terms of more minimal steps or departure from what you are doing, aren't there some deformations that break n equals 4 down to n equals 2? I remember Polchinski and others were doing, what were called n equals 2 star or something like that, which have more, richer dynamics, I would say, at least from, my standpoint.
Yeah, okay. So I think trying to understand n equals 2 star is interesting. In particular, n equals 2 star is massive, for instance.
Right. So,
well, first of all, there is known example of integrable mill theory with less supersymmetry, which is called beta deformation of n equals 4 supermills, which has n equals 1 supersymmetry. But that's not super interesting because that's again conformal. So the dynamics is more or less the same as n equals 4 supermills. And about going to the massive regime, not much progress has been made so far. But one thing one can try to do is to go to the Coulomb branch of n equals 4 supermills, which is a bit different from really going to the massive theory, but you can give some expectation value to some scalar fields. And that can be studied using integrability.
So in n equals 4, even in n equals 4, there was a problem. I don't know how well it has been solved. The problem of small black holes in the ADS-CFT correspondence.
Mm-hmm.
So the problem was to find states that correspond to black holes with radius much smaller than the anti-de Sitter radius, and find the right number, the ones that give you a exponential of the Bekenstein-Hawking entropy. So do you know what is the status of this problem and whether knowing the exact spectrum of a large class of operators helps in finding this small black hole?
I see. I guess one cleanest setup to try, one possible cleanest setup for addressing this question is to look at some supersymmetric black holes in ADS5 to S5, in particular 1/16 BPS black hole. But unfortunately, those states are not single trace. And furthermore, people don't really know how to write down the expression for the operator systematically. Yeah. But of course, there have been progress in the counting of the number of states which have that amount of supersymmetry, which was well, which is based on superconformal index. And I think people are recently trying to compute that superconformal index, which is given by some kind of matrix integral using various saddle point approximation. And I heard people are like, well, there was actually like recently a paper in which they found some saddle point, which looks like a small black hole, which looks like an analog of small black hole, but I don't quite know what the current status is.
Okay. So in this case, the integrability doesn't really help. It's more a different approach.
Yeah, well, there was an attempt to use integrability because, for example, suppose you want to construct some kind of near extremal black hole, like a near BPS black hole, then the structure of the Hamiltonian based on the spin chain is sometimes helpful, but I don't think there is concrete progress in that direction.
Thank you. Do we have other questions? Any? From students? So maybe just one, again, is historical. Maybe the simplest operator that has a large anomalous dimension is the Konishi operator. So do we now do we know what is the dimension? Because that's single.
Yeah, well, right. Yes, we can just plot it from like a weak coupling to strong coupling.
So that can be obtained with integrability.
Yes.
Thank you. Please ask. If there are no more questions, I mean, it's getting late, right? In Geneva, we should thank Shota again. And then I think that you may even have a meeting after that.
Okay, thanks.
Thank you.
Thank you.